Okay. It
That was my
started.
nickname in
So
high school.
yeah, okay. So this one's gonna be a little more confusing because like I said, it's a lot of like recursion and like to be fair, the topics they go over are like kind of advanced and they shove a bunch of stuff at you all at once. But like think of it as an introduction and then use the problems to like make sure you remember them. And then once again, be a little more familiar with your recursion. So like, I don't know, make like a basic recursive function that like calculates like n factorial or something because you're gonna need to like learn it for a lot of stuff in this section. So basically if we get started, complete search is in otherwise known as brute force. It just searches completely. So it's going to search the entire search space like and then just pick the most optimal answer. So like you're going to find every combination or every possible answer, choose the best one. So first off what they show us is subsets. So a subset is basically like choosing like a bunch of different elements from a set. They don't have to be like continuous or anything. So if you have 1, 2, and 3 in a set, the possible sets are nothing, only 0, only 1, only 2, 1, 0, 0, 2, 1, 2, and the whole thing. So notice that order doesn't matter in a subset. It's simply like the elements that you take. You either take them or you don't. So the first method that they show you is to use recursion. So what happens is if you have a vector that represents your current subset, so like it's not in this code, but let's assume that like outside of this function, like globally, you have a subset called, or you have a vector called subset. What happens is you have k representing how many elements you've iterated through. So you go from all of the elements from 0 to n. So if k is equal to n, then it means you've hit the end. So like you're done choosing all of the elements that you've wanted. So they put here just process subset. Otherwise, if you haven't reached the end, then you call um search on k plus 1 and you push back. So you have two options for every single thing, right? So what I this will come in handy later on. So let's say that we have a subset of 2, 3, 4. Um, uh, at every single index, you can either choose to take this or you can choose not to take it. So you have two options for this one. For this index, you can choose to take 3, you can not to choose 3, so another two choices, and then same thing for 4, so you have another two choices. So the number of subsets that exist for a given set is 2 to the n, where n denotes the number of elements in your set. So essentially what this code is doing is you're calling search assuming you didn't choose the kth element. So you're just calling search on k plus 1, and then you're pushing k. So like you're assuming you do take it, and then you call the recursive search function again. So this recursive call assumes you don't take it, and this one assumes that you do take it. And then what you do is you remove it after taking this so you can like process the rest of them. This way is a little harder. Once again, it's kind of useful to be able to do it, but like it is the harder method of uh generating subsets. So basically, here's your search tree. So like I said, at each step you have two choices. You either take it or you don't take it. So it branches out and you get the 2 to the end. So if you like check all the steps in the tree, you have
Yeah,
8,
yeah.
but or and n is equal to 3 and 2 to the third is 8. So the second set is using the bitwise operators like I mentioned. So what happens is if we know that there are, oh my god, I closed in pain. So if we know that there are 2 to the n subsets, right? For a given set, we can actually represent that using binary numbers or like what happens is we're going to implement from 0 all the way until 2 to the n, where each number we're going to take its binary representation and have that represent a set. So if we go for the most basic example of like 2, 4, 7, and you'll notice there's only 8, right? So maybe I should have planned this ahead of time. So the numbers from 0 to 2 to the n minus 1 are this, and maybe I won't, or actually no, that's all of them. So if we convert these to binary, you get 0, 0, 0, 0, 0, 1, and then I'll just speed through these. So if we do these all in binary, uh, yeah, that's all of them. So, this column correlates to if you take the first item. This correlates to if you take the second item, and then so on. So I equals 0 represents taking nothing. I equals 1 represents taking 7 because only the 7 is set to 1. 2 represents the set of 4. 3 represents 4 comma 7. 4 represents 2, and then so on, right? Are you getting it? So for each column, it represents if you take it or not. Make sense?
Yeah.
Okay, so in that case, this they just show you the code for it. So what happens is you iterate from 0 to 2 to the n minus 1. So they use bit shifting to get 2 to the n. And then what you do is you have to check if the ith bit is set. So the way they do that is they loop from 0 to n, and if b or if this right here, and the bitwise and of one shifted I is greater than 0, then it means that the ith bit is set and you're going to push this you're going to push the ith element into your subset. Um this is a little more like bitwise familiarity heavy, but like hopefully it makes a little bit of sense after like I don't know, like last week or something. But just kind of you might have to come back in references. The important part is just like you're getting um the ith bit from each value from 0 to 2 to the n minus 1. So if we move on next, permutations is basically it's basically a different like form of like generating all types of stuff. So let's say we have like I don't know like a set um 0, 1, 2. A permutation is basically like swapping all of the elements in every single possible way where every single element still exists in a permutation. So in a subset they're smaller. You just take a certain number of the original size. But a permutation is simply like taking the same set but trying every single order that exists. So right here they just show you that. So I'm gonna speed through this a little faster today, but this is once again the recursive method to do that. Um, all you need to do is if likewise to the generating subsets, if um if the size of your permutation is equal to n, then it means that like you're done, you've generated that given permutation. Otherwise, you write a loop from 0 to n, and you have an array that marks if an element is chosen. So if it's chosen, you can't choose it again, so you just continue. And if you finally decide to pick a certain element, then you mark it as chosen, you push it into the vector, and then you recall your recursive function. And then after this call finishes, you have to mark it as you have to unchoose it so that you can generate the rest of the permutations that don't have it selected. So you set it to false, and then you remove it from the vector that stores the permutation. The easier way is to use the std next permutation. So what you do is you just have a do while loop that that like calls the next permutation function, and you pass in the beginning and the end of your vector. It is important that this is a do while loop instead of a while loop, and the reason for that is a do while loop will like execute this part like before checking if it's valid. So if you don't have this as a do while, you're gonna miss like the first permutation. So it is important that if you're using this permutation, you write it as a do while. Um, so everything else in here is actually pretty cool stuff. They're like pretty cool problems that make use of these techniques. So first of all, this is a problem where like let's say you have like an n by n chessboard and you want to find all the ways to place a queen such that like or place queens such that they don't attack each other. So like this is a valid one, none of these queens attack each other, and then if you're not familiar with chess, queens attack up, down, left, right, and on all of the diagonals. So this is valid and this is valid for n equals 4. So essentially what you're going to do here is the way you solve this is you use next permutation and you try to place a queen. You know that you have to place a queen on every single on every single column here, but you don't know like which row to place them all at. So what you do is you have a vector that like I don't know is filled from like rows 1 to 8, and then what you're gonna do is you're gonna call next permutation to shift up which rows the queens are placed in. So they first show you the recursive solution. So it's pretty similar, but once again, y represents how many queens you have placed. So if y is equal to n, then it means you've placed all of them. So you increment how many valid solutions there are, and then you return. Otherwise, you go from x to n, where x represents that you're placing it on the x column. So it basically just checks that it checks that like the or actually they do it the other way around. They put it on the xth row and then they check that the xth column isn't visited and it's also not occupied on the diagonal. And if it's not occupied on the diagonal, it marks it and then does a recursive call and then it unmarks it afterwards. Um, they actually don't show the easier way to code it with next permutation, but I actually have that right here. So here's the code. It's a little ugly, but basically do while next permutation, check if it's on the bottom right or the top left to bottom right diagonal, and then check if it's on the bottom left to top right diagonal. And if there's no intersection, then it's okay, and you increment your answer. Um, this next one is calculating how many paths exist from the top left to the top right, where you visit every single square once. So this is a valid way, so like you just do any amount of curves. It's important that you visit every single square left or once, and then you reach the end cell, and then you can count it as a valid answer. So in a 7 by 7 grid, apparently there's like 100,000 possible paths. So this is something called pruning the search, where even though we're going over every single possible we're trying to go over every single possible answer, we're going to like cancel it early if we notice that it's no longer possible like for this to be an answer. And these optimizations will get it down in time. So if we just like literally calculate every single possible path and then have it get to the end, and then some of them will work, some of them won't work. The runtime will take like 500 seconds, and it'll take 80 billion recursive calls. So we're just not putting any optimizations in. It's just brute force. The first optimization that they show us is you're either going to move down or right, and then the rest of the paths are symmetric. So these two paths are symmetric to each other, so going down or going right. So what they're doing is instead of moving down and then right, you can just only move down and then multiply the answer by 2 because there's always going to be a symmetric path every time you go right. So this will only like cut your runtime and recursive calls in half. So yeah, it's like twice as fast, but it's not quite 1 second yet. So the next optimization is if we reach the end early and we haven't reached every cell, then we know that there's no solution because like we've already reached the end, so there's no way we can reach everything else and then and reach the end only once basically. So what we're gonna do is if we hit the lower left square too early, we're just gonna break. And once again, this will cut our runtime in about like half. But the most important optimization is it's a little complicated. If you like try to continue a path where you split the grid in half, then you just break out of like that search, like you just cancel it. So the example they give you is, for example, let's say we're trying to go straight from here, and you'll notice we hit a wall, and the left and the right are split up into like visible regions. It means that if we decide to go left from here, we're gonna visit everything here, and there's gonna be no way to hit the right side without crossing back over something we've already visited. And same thing with the right side. If we go to the right and we try to go left, there's no way to like visit everything without crossing over something that's already visited. So what happens is if we break early in this case, we go all the way down from 100 seconds to 1.8 seconds, and this is the best optimization that will we're going to need to be able to calculate this in time. This is also extended not only to like when you hit a wall, but also when you hit like any cell that's already visited. So once again, here you hit a visited cell, and it splits it up into a left region and a right region. Um, so once we do this, we should be able to run it in time. Uh, I'm gonna finish up here because you have to go soon, but here's the code for that. It's a little ugly, but basically I check if this valid will simply check if I'm like not running into a wall that will divide the rest of the grid in two. Meet in the middle, I'll skip over this real quick. Basically what you're doing is instead of checking everything, you're checking half of the elements and then checking another half, and then you're comparing them and then seeing if you can like get the answer from that. This is significantly faster because you're cutting in half, so when we're checking all the subsets of 2 to the n, our time complexity becomes 2 to the n over 2, which is square root 2 over n, which is a lot faster. And that's basically it. Me in the middle is a more advanced technique that I don't have a problem plan for, so maybe we'll go over this in depth another day. So
Don't they use
that's
that for like finding shortest points, like in 2D space, or shortest distance between 2 points?
I actually have no idea if it can be used for that. Meet in the middle is almost so like if you apply meet in the middle to like a polynomial like time complexity thing, you're only cutting the time in half, right? And I remember I used to say like, what's the point of meet in the middle? It's just cutting your time, like it's just like cutting your runtime in half, which doesn't change the time complexity. But the reason it's relevant for generating subsets is when you cut n in half when your like runtime is 2 to the n, you're not actually like cutting your operations in half. It becomes 2 to the n over 2, and as we can see, square root 2 to the n is not the same time complexity as 2 to the n. So I know
I
why
think
meet in the middle is
the
used for
point thing
this.
applies it repeatedly though,
Oh, it does. It's the
for
same
like
thing.
it does like meet in the middle, and then like in the left half it'll call like meet in the middle again and cut it in half until it reaches like a base case size. So it's kind of like divide and conquer, I guess.
Okay, that's a
But like,
that's a
yeah,
little. I see we're using
a
that
bit
as
different.
well. Yeah, I don't know if it would be that, but that sounds like it could be. So yeah, that's all of this section. So I think so just to go. So that's it for today. Problems are up.
Oh,
Um we'll do solutions later.